Okay, our next problem has a piston cylinder. It contains 4 kilograms of carbon dioxide and 6 kilograms of nitrogen. Is compressed in a polytropic process for which N is equal to 1.5. The starting temperature, 27 degrees Celsius, and the final temperature is 277 degrees Celsius, using variable specific heats determined. Okay, now, in last spring's test, I had 2 problems about ideal gas mixtures. You don't have that situation. That you have an isentropic problem. They did not have an isentropic isentropic. Let me make sure that they didn't have an isentropic problem. They had thermal efficiency problem. Yeah, they had 2 problems. They did not have an isentropic efficiencies problem. So you're going to need a study for that isentropic efficiencies problem. It's not going to be provided here on this practice test. Isentropic efficiencies. I have a whole bunch of problems there on the review module, but I think it's important for you to understand how to do these ideal gas mixture problems, because you're going to have one of the 2 types that we're talking about here. So I've been going through so many problems trying to get ready for your exam and reviewing. I forget which ones I have looked at and which ones I don't looked at. So this is going to be a closed system piston here, and we're going to have 4 kilograms of carbon dioxide and 6 kilograms of nitrogen here, compressed in a polytropic process. Okay, starting temperature is 27 degrees Celsius plus 273. Let's say that's equal to 300 Kelvin, and the final temperature is 277 plus 273. That's going to be equal to 550. Okay, Kelvin. Okay, using variable specific heats. So this is good. This is good. We're going to practice both constant and variable specific heats. We know that we have a relationship that PV to the 1.5 is equal to constant. Okay, because it is a polytropic process. So we get to remember all that, and we know that PV is equal to mRT. Okay, so my work is going to be equal to polytropic. Remember, P2V2 minus P1V1 all over 1 minus N. Or, because this is an ideal gas, we can write this as M total, R total times T2 minus T1 all over 1 minus N. We have to look at it as a total mixture. Now, we could find out what the work of the carbon dioxide is and the work of the nitrogen is and add it together. That's also a perfectly reasonable way to solve this problem. Okay, but I don't want to do that here. I want to find out what the mass total is. It's going to be 10 kilograms, 4 plus 6, no big deal. And I want to find out what the apparent molecular weight of my mixture is. And that's going to be the mole fraction of my carbon dioxide times the molecular weight of my carbon dioxide plus the mole fraction of my nitrogen times the mole fraction, or times the molecular weight of my nitrogen. Okay? So now I need to find out what my number of moles are here. So the number of moles of my carbon dioxide is going to be equal to 4 kilograms divided by the molecular weight of carbon dioxide, which is 44.01 kilograms per kilomole. And this gives me 0.0909 kilomoles. And the number of moles of my nitrogen is going to be equal to 6 kilograms divided by 28.01 kilograms per kilomole. And this gives me 0.2142 kilomole. Okay. And so my number of moles total is going to be equal to 0.0909 plus 0.2142. And now I have a total here of 0.3051 kilomoles. Okay, now I want to find out what my mole fraction is. So my mole fraction of my carbon dioxide is going to be 0.0909 divided by 0.3051, which gives me a mole fraction of 0.2979. And my mole fraction of my nitrogen is equal to 0.2142 divided by 0.3051. This is going to be equal to 0.7021. Okay, again, you add those both up, they should equal 1. So now I can find out what the apparent molecular weight is. That's going to be equal to 0.2979, or 0.79% of the molecular weight is going to be 44.01, and 70.21% of it's going to be equal to nitrogen. So we're going to lean heavily towards the nitrogen's weight, so we should be somewhere in the high 20s, low 30s, and what it ends up here is that it is actually equal to 32.78 kilograms per kilomole, which makes sense. Okay, so now with that information, we can put that into our equation, and we can say that the work is equal to, well, the total mass is 10 kilograms times our R value, which is going to be the 8.314 divided by the apparent molecular weight, which we just calculated is 32.78. This is going to be in kilojoules per kilogram Kelvin. And we're going to take it times our temperature difference, which I can put in Celsius or Kelvin, doesn't really matter here. Let me go here and go 550 Kelvin minus 300 Kelvin. Divide all that by 1 minus n, or 1 minus 1.5. And we are going to get a value of negative 1268.15 kilojoules, and that's our work that we have here, negative value. Okay, now good that we got a negative, because the problem statement said compressed. We're expecting it to be negative because we said compressed. Okay, now it's asking for the amount of heat transfer. Okay, closed system, we're going to have to say delta KE plus delta PE plus delta U is equal to Q minus W. Okay, and so we're going to say kinetic energy and potential energy effects are going to go away, and we're going to be left with here that Q is going to be equal to delta U plus whatever our work is. So what is going to be our delta U? Okay, so Q is going to be equal to, we can do this in moles or we can do this in mass. Now I'm going to go ahead and do this in moles and mass so you can understand this. That could be the number of moles of my carbon dioxide times U2 minus U1 bar of my carbon dioxide plus the number of moles of my nitrogen times U2 bar minus U1 bar of my nitrogen plus my W. I can do it that way. Or I could write this as the mass of my carbon dioxide times U2 bar minus U1 bar divided by the molecular weight of my carbon dioxide plus the mass of my nitrogen times U2 bar minus U1 bar all over the molecular weight of my nitrogen plus W. Okay, that's all, either way that we could do that. Okay, now I need some space here, more space. My thick pen is coming into here. I will just go ahead and do the way that I did it, because I like things in mass. I don't do things in moles that much, but again, it doesn't matter which way. I have the number of moles right up there at the top of my page. I probably should do this method because it's a little bit less writing, but I didn't. So I'm going to go with here what I have. It's equal to 4 kilograms times, if I look up these values, U2, it's 15372 minus 6939. Divide that all by 44.01 is going to be kilojoules per kilogram plus 6 kilograms times 11492 minus 6229 divided by 28.01 kilojoules per kilogram, and then plus my work, it's plus a minus 1268.15 kilojoules. Okay, and our units here are going to be kilojoules along everything, and so we're good to go. And so our Q here is going to be equal to 625.70 kilojoules. And so we are compressing this, and we are getting to that state. We're still going to have to add some heat to that. So that's what's happening. We're adding heat to the system, as though and we're adding, so two things. The surroundings are adding work. The surroundings are adding heat. That's what's happening in this problem. Okay, that's our second ideal gas mixture problem. Again, this one they were mixing to start with and mixing to end with. We could find out if you wanted to do this, good practice would be how much entropy is produced in this. And so you can find out what entropy is produced here now that we calculated Q. A little bit more work. But if you know how to do that, you are, and know how to do the previous problem, you are pretty well prepared for the ideal gas mixture problem on the exam. Let's stop that here. We'll go on to our next problem.